We are going to start talking about the sun, and the sun is our closest star. Our sun is 99.9% of the mass in the solar system, which is unbelievably huge. It pretty much is the solar system. Our sun is mostly hydrogen, 70% hydrogen, 28% helium, that leaves 2% for everything else. Our sun is 333,000 times the mass of the Earth, and that's how you read this unit here. M Earth means the mass of the Earth. It's also 108 times wider than the Earth. So you could fit 108 Earths across the sun, but if you imagine filling the sun, it's more like 1,000,000. You can fill the sun with 1,000,000 Earths. So our sun is incredibly huge. Here's a picture of the sun. In the visible light, you can see sunspots. There's little storms on them. If you switch to ultraviolet light or X-ray light, you can actually see solar prominences. So a big solar loop coming off the surface. And the sun's weather is bigger than our planet. The sun gives off an absolutely huge amount of power, 3.8 times 10 to the 26 watts. You might not realize how big that number is until you type out all the zeros. The sun puts off enough power that even though just a tiny bit of that hits Earth, it keeps our planet habitable. So the sun's mostly made up of hydrogen, and usually we think of hydrogen as a gas. So you'll have the hydrogen atom with a proton and an electron around it. But inside the sun, it is so hot that the electron has so much energy that it leaves the proton. So the sun, I imagine it as mostly hydrogen, but it's separated. The protons can do their own thing and the electrons can do their own thing. They're separate. They are not bound together as a gas. So I think of a plasma as a charged gas. Right? The electrons can move around without the protons. The surface of the sun is 10,000 degrees Fahrenheit. And that's the coolest part of the sun. So it's definitely hot enough for the electrons to be ripped away from the hydrogen nucleus. Our sun is kept in balance, and if it wasn't in balance, we would die. So what's balancing the sun is two forces. Gravity is always trying to squeeze the sun smaller. The layers of the sun will press down on the layers beneath them, and by the time you get to the center, there's a lot of gravity squeezing that core of the sun. If gravity was allowed to squeeze the sun as far as it wanted to, it would end up with a black hole. So we're lucky that there is a force that can support the sun against contracting any further, and that happens to be gas pressure. So the atoms of the hydrogen bouncing around into each other gives you gas pressure, and that supports all of the layers. The deeper you go into the sun, the gas pressure is higher because it has to support more mass above it from falling down. So I'm going to organize my lecture slightly different than maybe the book does it. I'm going to go and talk about each of the sun's 6 layers and just talk about the fusion as we're talking about the core, instead of having the fusion be its own section. So let's start off with the core, the first layer of the sun. It's 27 million degrees Fahrenheit and 250 billion times more pressure than Earth's atmosphere. I don't know what that means to me, except for I would die instantly. Those numbers are so big I have nothing to compare them to. Remember that fusion is taking a smaller atom and building it up into a larger, more complicated atom. So the core fuses hydrogen into helium. You actually need 4 hydrogens to build 1 helium, and the sun is going to do that through a series of steps that we call the proton-proton chain. So you don't actually have to know all of the steps in the proton-proton chain, but you should probably know that you need 4 hydrogens, and it's going to combine them into 1 helium with extra energy. So instead of labeling this a hydrogen, because it's a plasma and the electron's been ripped away, you could also just call it a proton. So you probably want to think of this as a hydrogen, but it's labeled a proton. So let's just start off with 1 proton, 2 protons, and they're going to fuse together. So you had 2 positively charged particles forced to be together, and there was too much pressure, and one of the protons gives up and changes. It reacts. So one of the protons converts and becomes a neutron. So now you've got a proton and a neutron together, and when that happens, it gives off a positron, which is a form of antimatter. It's basically just an electron that happens to have a positive charge. And here's a little neutrino. And we're going to talk about those more later in this chapter. But this positron is not going to be stable. If it touches any other electron in the sun, it'll turn into pure energy. So in a second, you're going to see it disappear into pure energy, into light. Now we're going to have another proton, another hydrogen come in and bind itself to this. This would technically be called helium because it has 2 protons, but it's not the stable form of helium yet, so we have one more reaction to go. This cluster is going to bump into this one and fuse. So there's your stable helium. 2 protons, 2 neutrons. This proton was used in the process, but it gets returned, so it can get used again, as does this one. So the proton-proton chain turns 4 hydrogens into 1 helium and some energy. Remember when we talked about E equals mc squared? All right. If you were to just weigh the 4 hydrogens beforehand when they were separate, 1, 2, 3, 4, if you weigh all the 4 hydrogens, they will have a certain weight, a certain mass. If you were to come back and weigh the particles after they have been bound together and fused together into 1 helium, they weigh less. And so some mass is lost in that reaction, and that's where the energy comes from. The amount of mass lost goes into the equation E equals mc squared, and it tells you how much energy the sun is generating. If you want to fuse 2 hydrogens, 2 protons, you have to get them close enough together before the strong nuclear force can actually bind them together. But a positively charged object does not want to be next to another positively charged object. So if you were having the 2 protons approach each other at normal typical speeds, they actually end up repelling and they will not get close enough to fuse. So this is why nuclear fusion doesn't happen in the core of the Earth or even in the upper layers of the sun. It's not hot enough and the particles are not moving fast enough. So only in the core of the sun is it hot enough, which makes these particles move fast enough that they slam into each other faster than they can repel, which allows it to fuse. So you need the high temperature of the core of the sun to let them get close enough together to fuse. And you also need the high pressure, because if you didn't have the pressure pushing down on the core of the sun these kinds of temperatures would just expand the gas out into space and poof, it would cool itself off. So the high pressure keeps it at a high temperature. All right. So now let's talk about the solar equilibrium, or the solar thermostat, how the sun controls its own internal temperature. If the sun heats up a little bit in the core, that means the particles are moving around faster, and that will let fusion happen more rapidly, which will make it even hotter. So that could be a problem. If it gets too hot, it's going to get even hotter. But the sun is stable, so there's actually a feedback mechanism which brings that under control. And that is because the core can expand and contract a little bit, and expanding, when a gas expands, it takes energy and that cools it down. So the core can expand and contract to keep its temperature stable. So let's follow the right loop here around and talk through it. Let's say that the core gets a little bit too hot. That means the particles are moving too fast. They'll slam together even harder and make fusion rates increase. Fusion rates increase, the particles move even faster. Pressure will also increase. But now you've got the balance between gravity and pressure. And now you've just made pressure a little bit stronger. So it can expand a little bit against gravity. So the core can expand outwards against the gravity, and that will expand it and cool it to a new stable temperature. Okay. This left loop is pretty much redundant, but I'll talk through it anyways just so you can hear it again. Let's say that the core is too cool. The fusion rates will decrease, which will make it even colder. The particles will move less quickly, and that also affects the pressure. The pressure goes down. Okay. But now you've got the balance between gravity and pressure, but the pressure decreased. So gravity can win, and gravity will squeeze the core, which also heats it. So now you have reheated the core by letting gravity squeeze it just a little bit. The sun goes through almost 600 million tons of hydrogen a second, and it loses about 4 million tons a second while it's generating that energy. So it loses 4 million tons a second, but that's nothing to the sun. It doesn't really even notice. The orbit of the Earth doesn't even notice. It's not a big deal. So let's estimate that 1/10 of the mass in the sun can be used as fuel. Do a little ratio. Lets you estimate roughly how long the sun can shine. About 10 billion years. That's a pretty good estimate. We think our sun should last about 10 billion years. We're about halfway through that though. So let's move to the next layer. So let's move out of the core. Move out of the core to the radiation zone. Okay. It's called the radiation zone because light is trying to escape the core, and light is a type of radiation. So this is the energy in the form of light is trying to escape, trying to get to space. So the light is trying to get out by traveling in a straight line. But when it travels in a straight line, it's going to run into another hydrogen or an electron. It's going to run into something. And when it gets absorbed by a particle, it will have to get re-emitted so that energy can try to get to space. But every time it gets re-emitted, it gets re-emitted in a random direction. So it's not going to make a nice straight path out of the sun. It's going to end up zigzagging around. And we call the zigzag a random walk. The light is being forced to travel in a zigzag path, which makes it really inefficient for this energy to get out. Rough estimate, it might take 100,000 years for one piece of light to escape the radiation zone. 100,000 years. So this little animation is actually computer calculations. Piece of light always trying to escape, but every time it moves a millimeter, it hits a new particle and it has to change direction. In the third layer, the convection zone, the energy is trying to escape in the form of convection. So the energy is coming up from the radiative zone and it gets absorbed into the convective zone. And the gas in the convective zone is able to hold on to that heat for a little bit longer. It doesn't have to play hot potato with it before and make a zigzag path. The gas can hold on to the energy. That makes the gas or plasma less dense and it bubbles up, floats up. So the convection zone is kind of like a great big conveyor belt. The hotter gas holds on to the energy, takes it up to the surface, and it releases it to space. Once the gas is cooled off, it's a little bit less dense and it sinks back down to repeat the process. So this is actually much more efficient, getting the energy towards space. So if you estimate how long it takes for some energy to get through the convective zone, instead of 100,000 years, now it's only 10 days. The fourth layer is called the photosphere. And I should mention that the photosphere is considered the bottom layer of the atmosphere. So from here on out, we're actually going to be talking about the atmosphere of the sun. So these are layers that some light can just travel through. The photosphere is best known for being just the right temperature that emits visible light. And so this is the layer of the sun where visible light is free to go to space. We see the photosphere as being the surface of the sun. So here's how the sun would look to us if you could look directly at it, but please don't hurt your eyes. You would see sunspots. The photosphere is incredibly thin. It's like the skin on an apple. So if here's the bulk of the sun underneath it, the photosphere is this tiny little white line running across, and the next layer of the atmosphere is above it. So the sun, to us, looks very round and contained and smooth because the photosphere is such a smooth, even layer. But the upper layers of the atmosphere are not going to look quite so smooth. Some other things about the photosphere. This is roughly 10,000 degrees Fahrenheit, so this is the coolest layer yet that we've seen for the sun. And if you were to zoom in on the photosphere, you would actually see evidence of those convection cells from underneath. The hotter material rising up is brighter because it's hotter. And so that might be this little bright cell right here. And then once the gas cools off, it's a little bit darker and it'll sink back down. And that's always churning. So that if you were to zoom in on the photosphere, the sun always looks like it's churning. These really dark spots over here are sunspots, and we'll talk about those later. The second layer of the sun's atmosphere is called the chromosphere. And the chromosphere is best known for having the right densities and the right temperature for it to emit ultraviolet light. So if you get a sunburn, blame the chromosphere, okay? The chromosphere is actually hotter than the layer beneath it. If you had an ultraviolet telescope, this is what the sun would look like. But humans can see the chromosphere in the case of a solar eclipse. So if you were to just look at the sun typically, or with proper equipment, I should say, usually you'll see the photosphere because that's the brightest part. But during a solar eclipse, the moon can perfectly block out the photosphere, which will let you see the chromosphere just peeking around the edge of the moon. The sixth layer of the sun is called the corona. This is also the upper atmosphere of the sun. The corona is even hotter than the chromosphere, 1.8 million degrees Fahrenheit. It's amazingly hot. but it's not very dense. So it means that it's not the brightest part of the sun. We still see the photosphere as being the brightest part of the sun. But if during a solar eclipse, here's the moon perfectly blocks out the other layers of the atmosphere because they're brighter. You got to block out the photosphere and you've got to block out the chromosphere. Then you can see the corona during a solar eclipse. So that's this wispy material out here around the solar eclipse. The corona has the right temperature to emit mostly X-rays. So if you want to look at the corona when it's not a solar eclipse, I would suggest getting an X-ray telescope. And when you look at the corona in X-rays, it'll look something like this over here. The last part of the sun that we're going to talk about is called the solar wind. But you have to be careful because the solar wind is no longer part of the sun. These are particles that escape the sun and they're traveling out into space. So the solar wind are particles, protons and electrons, and they stream outwards into space. They can travel at 1,000,000 miles per hour. Most of them will just go out through the solar system. A few of them, though, will end up hitting Earth's magnetic field, and if it hits it just right with enough intensity, we can end up getting an aurora. One of the ways that we know what's actually happening inside the sun is by watching how waves travel through the sun and affect the other side of it. So one of the things that people do is called helioseismology. It's basically watching sunquakes travel through the sun and affect the surface. And by watching how fast the waves travel, you can figure out how long it takes to go through the sun, and that depends on temperature and pressure. So you can figure out the temperature and the pressure inside, the different layers and the different structures. There's one more way that we can actually see what's going on inside the sun in real time. So light is trapped by all the gas and all the plasma. So the light is in here doing a zigzag path. But do you remember the neutrinos? They were created during the proton-proton chain. But once a neutrino is made, I call it a ghost particle. It can go through the entire core of the Earth, and it just doesn't stop at all. It just goes through the core of the Earth. A neutrino is made in the core of the sun, and it can just go through all of the plasma without stopping. It doesn't matter to it. There are literally, truly, about 65 million neutrinos who pass through your fingernail every second. Out of all of those 65 million that go through your fingernail every second, maybe a few a year will stop, will interact with your thumbnail. And so that's how we can observe neutrinos, is we will wait for one neutrino out of trillions to interact. So we build detectors now to catch these rare neutrinos that will randomly interact, and we can actually observe neutrinos coming from the sun. And remember, neutrinos are created from fusion, so you're actually able to see the fusion rates inside the sun now. It's pretty amazing. When we first started detecting neutrinos a couple decades ago, we were not measuring enough. We were losing neutrinos. We couldn't figure out why we were not detecting enough neutrinos. It turns out that these tiny, tiny, tiny little particles are so low mass that they are able to change flavors or switch types. So the sun creates what's called an electron neutrino. But in the several minutes it takes to get from the sun to the Earth, some of them will switch flavors or switch from an electron neutrino to a different type. And so that's why we weren't detecting enough electron neutrinos. We have now used this to confirm that neutrinos can just change their flavor mid-flight. It's strange, but why should everything out in space make sense?